Hello, everyone. My name is Marko. I'm coming from University of Zagreb, from Croatia, Faculty of Electrical Engineering and Computing. My area of research is related to the development of technology for landmine detection. Today, I will talk about rapid object depth estimation from position reference EMI data using machine learning. EMI stands for electromagnetic induction. So first, let's start with problem statement and motivation. Metal detector is a standard tool used in demining. It works on principle of electromagnetic induction. Besides that, it's used in other applications such as security systems, treasure hunting, etc. On the one hand, it is quite good at providing information on presence or absence of metallic objects. But other than that, for example, it is not able to precisely locate the object. You can you can pinpoint horizontal coordinates to a reasonable accuracy, but object depth is very difficult to estimate. Why is this important? For example, in demining, object depth would be very important in terms you can do coarse object discrimination with that. For example, anti-tank landmines are buried deeper than anti-personnel landmines, and also it can help with extraction of electromagnetic features, which can then be used for discrimination purposes. Something about the principle of operating principle of metal detector. So it operates on principle of electromagnetic induction. So time varying magnetic field reacts with metallic object, which then creates secondary field, which is detected by the receiver coil. If the magnetic field is homogeneous within the object volume, we can replace it by small magnetic dipole. This means that we can use this formula to calculate the object response to magnetic field, and the object response is dependent on the H, Tx, Rx, which are purely geometrical terms, depending on sensor object system geometry. So relative pose between sensor and object and sensor geometry itself. And it depends on M, which is magnetic polarizability tensor. Essentially, it contains object intrinsic features and spatial orientation of the object. These lambdas, or object intrinsic features, we can explain them like sensitivity of the object to the primary field in different directions, X, Y, and Z directions. And those are used for discrimination purposes, metallic object discrimination purposes. And they depend on material size and shape of the properties of the object. Here is the flowchart of the proposed solution. Something happened with this. It's flipped, but okay, I'll try to explain this. Okay, so the proposed solution uses it uses the line scan data. So one pass over the object is enough to estimate the object depth. So it basically uses a CNN, convolutional neural network model, to do so. This is brief description. I will go into details. And we use as a benchmark method the nonlinear least square method, which is well-established approach to estimate the object location and object features from the measurements, a bunch of measurements over the object. So the problem with this nonlinear least square method is the strong correlation between object depth, object location or object depth, and intrinsic features. So here, this is the dipole model approximation formula used to construct training dataset for the algorithm. So we must model each variable. first variable is magnetic field, which is a function of geometry, line scan, trajectory, and object location. So geometry is known. Trajectory is defined along y-axis. So in a range between minus 23 and 23 centimeters with a step of half centimeters, and it's fixed. Location is set to 40 linear space depths between down to 15 centimeters. And after we calculate line scan, we divide it by its maximum value, so the constant k becomes irrelevant. Now what's left is to model the tensor M, which contains the spatial orientation of the object and the eigenvalues. Eigenvalues, as said, are intrinsic features. So what we want to achieve, we want our algorithm to estimate the same depth regardless of object orientation and its intrinsic parameters. So angles, we define predefined set of angles with the resolution of 22.5 degrees. And we use each combination of pitch roll and yaw angle in the training data set, and eigenvalues are modeled in such a way that we try to model all possible ratios which are reasonable for different metallic objects. So ratios of these eigenvalues. So one eigenvalue is set to 1, and other two are set to different combination of the predefined set of values. And we do that for each eigenvalue. So each instance is calculated for each depth and combination of orientation and set of eigenvalues. So we perform scaling, and instance has 93 features, and the depth is corresponding label. So depth estimation is done using 1D convolutional neural network. So convolutional neural network is employed to extract depth specific features. So we assume that these features regardless of the type of the object and orientation of the object, when we scan over the object, it will contain spatial features which are characteristic to that depth. And CNN is employed to extract those features. And we use classification in this version. We use a feed-forward network classifier within 17 classes, and the estimated depth is weighted average of the probabilities. So to make sure that everything is done correctly, or I didn't mention that when we pass over the object, there is a problem. We can pass too fast, or we can do bumps during the pass over the object. This can affect the estimate. So to avoid that, we do another estimate. Algorithm waits for another estimate from different line scan. And if those estimates are do not differ too much within, or they are within the predefined threshold, we say, okay, the measurements are valid. So the depth estimate is the mean value between those two. So training is done on 125,000 line scans, split into two parts, training and validation. And selected model is one that minimizes the validation loss over first 40 epochs. So here's the experimental setup. Within scanning area, we do sideway motions with metal detector following the scanning pattern during the period of 60 seconds. So for nonlinear least square method, we use data from the entire measurement to find the object location and object intrinsic parameters and spatial orientation. For the proposed model, we extract line scans with the highest amplitudes, because those are line scans which are close to the origin or which are directly above the object. So, and then used for depth estimation. Here is the tracking system which is used to provide pose of the metal detector search head during the measurement. Test dataset which is used contains objects of different sizes, shapes, and material properties. In total, 314 measurements. Experiments is done to evaluate the performance. And sorry, here are the results: comparison of the proposed thin base model and non-linear square method. First two figures show the PMA2 and PMA1 fuse, which are hollow cylinders having the same geometry but different sizes. And those are non-magnetic. Both algorithms perform well. You can see that. So at the x-axis are depth regions of the estimation. So on the right side is deeper depth. So we can see that both algorithms perform well for these two scenarios. So with median absolute error within 1 centimeter almost for all cases. But for the plate-like objects like bottle cap and 50 cent, you can see that CNN-based solution outperforms NLS inversion, which can be seen at larger depths. The effect is even more pronounced for the steel cylinder and steel ball. The reason why this is happening is I mentioned that NLS method estimates object intrinsic parameters and location at the same time, which are strongly correlated. So at larger depths, we have lower SNR. Lower SNR means that NLS has a greater chance to get stuck in local minima. So it performs worse than the proposed method. And here is the first possible application of the method. We can use it to fix the depth of and help NLS method to extract better features which can then be used for discrimination purposes. So that's it for me, at least for now. Thank you.